Hey guys, what's up? Welcome back. So we're going to finish up Learning Guide 16.2 today and talk about the relationship between equilibrium solubility and how it relates to whether or not something will or will not dissolve and whether or not a precipitate will form. So we're going to be looking at the relationship between equilibrium constant and reaction quotient, specifically as it relates to solution chemistry. So starting with this, let's take a look first at the relationship between Q and K as it relates to equilibrium that we've studied already back in chapter 14. So back in chapter 14, we looked at how it relates to a reaction. So if we're talking about a reaction, when Q is equal to K, that means that the system is at equilibrium. We learned that in chapter 14, if Q is greater than K, it's gone past the point of equilibrium. And as a result, that means it has to work its way back to equilibrium, meaning that there's too much product, not enough reactant. So the product has to go down, reactant has to go up. So it's going to shift left until the equilibrium is met by the reaction quotient. Conversely, if at any given moment K is greater than Q, that means the reaction Q hasn't reached equilibrium yet. So the reaction has to proceed in the forward direction until the products increase and the reactants decrease, and that quotient of products over reactants equals the value of K. So how does this relate to solution chemistry when we're talking specifically about slightly soluble salts? Well, if we're talking about a solution, if Q is equal to K, that means we've reached a saturated solution. Remember, in our study of solution chemistry, a saturated solution is one that's at equilibrium and it's reached the maximum amount that can dissolve at a given moment. If Q is past K, that means that you've got too much product relative to reactant. Meaning, in other words, when we're talking specifically about salts, a precipitate's going to form. Conversely, if K is greater than Q at any given moment, that means the reaction has not yet reached equilibrium. It could still dissolve more, and the reaction is considered unsaturated at that moment. So if you remember going back to our study at the beginning of the year of how concentration of solution relates to spectroscopy, and when we were studying the concentration of solutions relative to the color of the solution and how much light was either absorbed or transmitted through a solution, when we made our Beers-Lambert law curves at the beginning of the year, we spent a lot of time at the beginning of the year using the formula M1V1 equals M2V2 to determine how the concentration of a solution changes during the mixture of two solutions or the diluting of a solution. We're going to do a lot of that in the upcoming slides as it relates to the relationship between Q and K. Let's go over a couple of examples so that you can see what we're talking about. So for example, let's say we got a beaker, and in that beaker, we currently have 200 milliliters of 0.004 molar barium chloride. And in addition to that, we're going to mix 600 mils of 0.0080 molar potassium sulfate. Now, technically speaking, solutions are not additive, meaning that 200 plus 800 does not equal, or 200 plus 600 does not equal 800. But when we're talking about solutions that are as dilute as these, we're talking about molarities that are 10 to the negative third factor. In situations like this, the solutions are so dilute that you're essentially mixing two aqueous solutions that are so much more aqueous than they are solute in nature that the additive properties are consistent. So 200 plus 600 milliliters essentially does equal an 800 milliliter solution when it's this dilute. So if we were to take these two solutions and pour them into the same beaker, we would have, for every 1 mole of barium ions, we'd have 2 moles of chloride ions. And for every 2 moles of potassium ions, we would have 1 mole of sulfate ions. So hypothetically, if we were to mix these two solutions together, the first thing we need to do, we need to figure out what is the potential insoluble precipitate. So that means we would have to use our solubility rules to determine which combination of these ions in solution would form an insoluble precipitate. Now we know from our solubility rules that potassium ions are always soluble. So potassium is going to be soluble with any negative ion found in this solution, whether it's chloride or sulfate. And it must be soluble with chloride because we started with a solution of barium chloride. Now, if we take a look at the solubility rules as it relates to sulfates, sulfates, generally speaking, are soluble. But one of the exceptions is when it combines with barium, right here. So when these ions are in solution, the only potential precipitate would be the barium combined with the sulfate. So what we need to do is we need to compare the amounts of barium ions and sulfate ions in solution at this given moment to the equilibrium constant to see whether or not it would or would not dissolve. Is it saturated or past the point of saturation? So based on the ions present, we know that barium and the sulfate would combine to make barium sulfate if the concentration is high enough. We need to see if that concentration is high enough based on these two combinations. So looking at barium sulfate's solubility, we would take the equilibrium constant. So equilibrium is products again over reactants. So we would take the barium ion and the sulfate ion, the two ions involved, and set them equal to Q instead of K because we don't know if this is at equilibrium yet. The first thing we're going to do is we're going to look at the barium ion, which is in red. So initially, the molarity of barium is 0.0040 molar, and we had 200 milliliters of it. We added 600 milliliters of another solution to come up with a total volume of 800 mils. So the molarity of the barium ions after the mixing of the two solutions is 0.0010. Now we have to independently look at the sulfate ion. So we're going to set up another M1V1 equals M2V2, except this time it's going to be for, in green, the sulfate ions. So the initial concentration of the sulfate ions was 0.0080, and we had 600 milliliters of it. If we change the total volume to 800 milliliters, the molarity of the sulfate ions in the end would be 0.0060. So remember, on dilution, concentration always decreases. This went from 0.0040 to 0.0010, and the concentration of the sulfate ions went from 0.0080 down to 0.0060. It's always going to go down in a dilution. So now if we take the concentrations of the barium and the sulfate that we've solved for here and plug them into Q, 0.0010 times 0.0060, we get a Q equal to 6 times 10 to the negative 6th. Now, the only way we can tell whether or not a precipitate's going to form is if we compare it to K, which again, remember in the last video, I told you guys that you can find this information in your books on page 737. So the KSP for this salt is 1.1 times 10 to the negative 10. So you can see that the Q here, 10 to the negative 6, is a factor of 10 to the 4th greater than the K. So it's much greater at this point. So because Q is greater than K, it's gone past the point of equilibrium, and that means that a precipitate would form. So you'd have a small amount of barium sulfate forming at the bottom of this container. Let's take a look at another one. All right, so again, I have my beaker. I'm going to add 2 milliliters. That's it, just 2 milliliters of 0.2 molar sodium hydroxide. And I'm going to add that to a full liter of 0.100 molar calcium chloride. So that means that upon mixing, I got sodium ions, hydroxide ions, calcium ions, and chloride ions. First thing we need to do is we need to look at from this model that we've created here on the left, what possible combination of ions would form an insoluble precipitate. So again, if we use our solubility rules, sodium ions are always soluble. So it's going to be soluble with the hydroxide and the chloride. So we got to figure out, is the calcium soluble or insoluble with hydroxide? Well, according to the solubility rules, it's slightly soluble. So that calcium hydroxide has the potential, depending on the concentrations of the 2 ions present, to form a precipitate. So at this point, we got to use the information in our textbooks found on page 737 to see if this calcium hydroxide will form based on these original amounts. To start with the calcium ions. So initially, the molarity of the calcium was 0.100 molar. We had a liter of it. We added only 2 milliliters of sodium hydroxide. So the total concentration went from 0.1 molar in a liter to a new concentration of 0.0998 molar in a total volume of 1.002 liters, or 1,002 milliliters. Now we got to do the same thing for the hydroxide ions. So according to our information over here in red, we mixed a 0.2 molar hydroxide solution with a volume of 2 milliliters, and we diluted it to a total of 1,002 milliliters. So it doesn't matter if it's in milliliters or liters, as long as it's consistent. So if we solve the new molarity turns out to be 0.000399 molar. So it went from 0.2 molar all the way down to a concentration of 3.99 times 10 to the negative 4th molar. So now we're going to use our equilibrium expression. So calcium times hydroxide raised to the second. And remember, the reason we're raising it to the second is because there's a stoichiometric coefficient of 2 in front of it. So if we plug in the 0.0998 in green and the 0.000399 in red and solve for Q, upon mixing, the equilibrium or the reaction quotient is 1.5 times 10 to the negative 8. Now, how does that relate to K? Remember, back in your textbook to page 737, the value of K for this is 8.0 times 10 to the negative 6th. So 10 to the negative 6th is about 2,000, or I'm sorry, is about 100 times greater than 10 to the negative 8th, but that's got a smaller number in front of it, meaning that K is greater than Q. So just adding 2 milliliters to that liter of solution, no precipitate's going to form. Gets close, but it's not there yet. You can still add more until a precipitate forms. So that's how K and Q relate to one another using M1V1 equals M2V2 for both ions independently and then combining them in the Q expression. Now, what if we had a combination of ions in solution and we added another ion to it and we wanted to know which one forms a precipitate first. For example, let's say that we had a solution that had a mixture of chloride ions and bromide ions in it. And each of those ions had a concentration of 0.020 molar. And let's say that we added to it some solid silver nitrate. Because it's a solid, it's not going to change the volume of the solution appreciably. So the total volume is going to stay the same. If we were to do this, which one of these two ions would form a precipitate first? Now, if we take a look at our solubility rules, both chloride ions and bromide ions are insoluble when they combine with silver, but one has to be more soluble than the other. So each of these ions has the potential to combine with the silver ions that I'm adding to the solution. But which one does it first? Well, the silver and the silver chloride would produce, or the silver and the chloride would produce silver chloride, and the silver and the bromide would produce silver bromide. Taking a look at page 737 of our textbook, we see that the solubility product, or the equilibrium constant, for silver chloride is 10 to the negative 10th, while silver bromide is 10 to the negative 13. So based on these two values, which one is less soluble? Well, the one with the lower K is going to be the one that's less soluble. So that's going to be the one that forms the precipitate first. But how much sooner does it form the precipitate? Well, let's start with the silver bromide first. If we start with the silver bromide, KSP equals silver times bromide. The KSP is 7.7 times 10 to the negative 13. I already know what the concentration of the bromide is in the solution. It was 0.020, which was in blue over here on the left. So I can solve the concentration of the silver ion necessary to form the precipitate. So silver is going to form a precipitate when the silver ions reach a concentration of 3.9 times 10 to the negative 11th molar. Now, if I do the same thing for the silver chloride, again, I already know the concentration of the chloride that I've added to the solution already. 0.020. And I solve again for the silver ions. The silver ions will not form a precipitate with silver chloride until the concentration gets to 8.0 times 10 to the negative 9th molar. So if we're comparing these two molarities, we see that silver bromide is going to form first because it has a lower solubility before it starts to form a precipitate, compared to the 8 times 10 to the negative 9th. So these little crystals that are forming in the solution first, those are going to be crystals of silver bromide. And the silver bromide is going to continue to form until this dilute solution reaches a concentration of 8 times 10 to the negative 9th. Then both solids will start to form. Last one. So let's say that in a solution, I add silver ions again in solid form to a solution containing 0.1 molar chloride and 0.1 molar phosphate. What I would ask you guys to do now is pause it and see if you can work through a problem modeled similar to this one, where you determine which of the two would form a precipitate first and what two concentrations are necessary for the precipitates to form. So take a moment, pause it, grab a sheet of paper, calculator, and try to do this problem yourself. Then when you're done, unpause it, and let's take a look at whether we did it right or wrong. All right, let's take a look. So is the silver going to start the silver chloride or the silver phosphate? The KSP of silver chloride is, again, 1.6 times 10 to the negative 10. Silver phosphate is 1.8 times 10 to the negative 18. So if I work through the KSP just like we did on the previous problem, so this is exactly the same as this previous problem. We just changed the concentration to 0.10. Silver ions will start to precipitate when the concentration reaches 1.6 times 10 to the negative 9th molar. Now, what about the silver phosphate? Be careful and make sure that you raise this to the third power because of the 3 silvers that form. So I plug in the initial concentration of my phosphate ions, 0.10, solve for silver ions. Remember, take the cube root. We get 2.6 times 10 to the negative 6. So you might have thought initially by looking at these 2 KSPs, oh, this is much less, it's going to precipitate first. But you got to remember that for every silver phosphate, it takes 3 silvers to form the precipitate. It's a 3-to-1 ratio. So the reality is that this is going to form a precipitate first because it has a lower molarity necessary of silver ions to start these 2 to combine with one another in terms of entropy. The silver phosphate would be second. All right, that's it for this one, guys. We got a couple Pogles that we're going to work on next. I'll talk to you guys soon.